Okay, in this video we'll just describe how you do the shooting method when the equation isn't linear. Now you can say, like, how do you check if something is linear? Well, that's not really the way you'll be thinking. I suppose essentially it'll be linear if the method, the shooting method that we looked at, where you take the two shots and you average the slopes, if that works, it works. It's probably the way I'd look at it. If you try it with this, it won't work. So we need a different method of looking at this. So let us look at this again. This is a boundary value problem. You know about t, the function you're looking for at 0 and 10. They're the boundaries. It's a heated rod. And the problem is our Euler method, for example, cannot handle this exactly. With Euler method, you write this as two first-order differential equations. We have to do that anyway. And we have a starting value of t, but we've no starting value for v, which would be a variable that we say is the first derivative of temperature with respect to distance. So, okay, let's write this as two first orders anyway. Let's see where we are after that. Okay, so as usual, you let v be the first derivative. Now, often this v has some meaning in terms of, say, if this was distance, this would be velocity. If this function here is bending moment, this is shear. Here it doesn't have as much meaning, but I suppose temperature gradient you could call it. Okay, if we differentiate both sides of this, we find that dv dx is equal to the second derivative of temperature with respect to x. And if we do this, we can write this as two first order differential equations. A differential equation for t, which is essentially here, and if we substitute the second derivative here equal to dv dx, we will also have a differential equation for v. So let's see, what are we going to do? So dt dx, the differential equation for the temperature, dt dx is equal to v, together with a starting value of t of 40. That starting value t is taken from the question. And now, as I said, this is equal to dv dx. Add this to both sides. I'm a little worried about this sign, but we won't worry about it. dv dx is equal to this. Add this thing to both sides, and you end up with 5 by 10 to the minus 8 times 20 minus t, which is, this t, by the way, is t is a function of x. I probably would maybe like that written as t is a function of x, but down here t is fine. But the issue is we do not know the starting value of v. The starting value of v is we don't know. What makes this not linear? What makes both take two shots, average the two slopes out, and weighted average? This power of 4 means this thing is nonlinear. If this is t to the power 1, then that other thing wouldn't work. Okay, what are we going to do? So we're probably going to shoot straight at it initially. So we'll just we'll do a little graph here. So here's x, here's temperature. Always label your axes. 0, 40, 10, 200. So if we were to shoot straight at it, you do a bit of rise over run, shooting straight at it. Now we're still going to have to, you see, the issue here is we're not going to take two shots and average them out. What we have to do is take loads of shots. And there's other approaches you can take. You can use, I can't remember the name of it, but when you cut the bisection method, you can do that. You could start with a very small slope and increase it by a step size and look at which one is closest. All these things are reasonable. But what we're going to do here is we're going to, in a certain sense, try loads of different starting slopes. Now this one, rise over run, I see 160 over 10. So a reasonable start is 16. I'm not sure if I should do that on the next page, but that's a reasonable shot, shooting straight at it. So you look at this on the next page. Now this one, okay, I've ruined it as such. I've started with 10, which doesn't necessarily make any sense, which we won't worry about it. It actually doesn't matter. So this is something, you want to take loads of shots. You want to do this in Excel, not in VBA, where you can use this goal seek function. So let's see what I've done here. On an Excel worksheet, we solved the problem using Heinz method. Now in Heinz method, if we're not doing it like Runge-Kutta, we've got V, we've got T, we've got a V predictor and a temperature predictor. You wouldn't do Runge-Kutta style Heinz method in Excel, but in VBA. But we don't have, as far as I know, goal seek inside in VBA, so we need to do it on the worksheet. So yeah, we do Heinz method here. And with a starting value of V, which would have been way up here at the top of the V column, we end up with a temperature of 233. Now what we were trying to hit, if we look back at the question, the temperature at a distance of 10 is supposed to be 200. So this is an overshot. But what we can do is, we can say, okay, Excel, please try loads of different values of the initial slope until this is equal to 200. So set this cell D102, which is this, equal to 200 by changing B2. And this B2 is the V0. So what this is going to do, the sound effect is obviously, it tries loads of different values of this, and it keeps trying loads of values until it gets 200 here. How it works exactly, we don't have to worry about. Maybe think about how it might work. And it turns out that if you try loads of different values of V, it works if you have an initial slope of 9.316. So it actually wasn't that far off initially. And then we run it again. Well, actually, we don't have to run it again because it'll be right in front of us. Like when it does this, in the end, it'll put in the 9.316 here, and you have approximately 200 here, and you see this thing here. Now, I think it's probably worth pointing out that I think this model, I think it is also set up so that there's room temperature 20. So the temperature of the air is 20. And you see, because it can't kind of go, you see, it's kind of being dragged down to the air temperature here, but the point is it has to eventually get up to 200, and it'll happen most dramatically there. What is the mechanism between it, about it being power 4, I don't know, and I'm not going to pretend I know. I'll just drive on. So this is goal seek, where rather than taking 2 shots and averaging them out, you try loads of shots using Excel. You can, of course, still use goal seek, even if the linear method works. The linear method, by the way, is you take your 2 shots, average them. You can still do goal seek, even if the differential equation is linear. And probably what I've described that as, an analogy is if you have a quadratic equation, you can solve it, the nice problems, using factorization. And if you can't factorize it, you use the minus b formula, but you can actually use the minus b formula all the time. Same thing here. You can use the linear shooting method, 2 shots. If it's a nice problem, if it's not a nice problem, you have to use goal seek or something like it. Well, let's say goal seek, but you can actually still do the other problems using goal seek as well. Now, the problem is, if you want really accurate results with a linear differential equation, you're going to want to go into VBA and use Runge-Kutta 4. And I don't know if the goal seek is available for use in VBA or not. Okay, so we'll just do a little example of this. There's no harm seeing the example of writing the second order as 2 first orders. My suggestion is, from the written exam, most of us will have most problem there. Okay, so this can also be used for linear ODEs, and this is linear because this isn't the power of x, or isn't a power of x. So consider a particle of mass 200 grams subject to a spring force with a spring constant of 5. This explains where the 225 comes from. Ma equals minus 5, and the m is 0.2. Divide both sides by 0.2, or multiply both sides by 5 to kill that. And then the 5 divided by 0.2 will give you 25. what velocity must the part, okay, this is weird, this is actually a design problem. This is a slightly design problem, which is where we saw actually goal seek initially. So it's saying what velocity must the particle start off with if the spring is to close to equilibrium in 0.5 seconds. So this is a design problem. It's saying, okay, I have a spring. I need it to close in half a second from an initial displacement of 1. I need it to go to 0 in half a second. What is the initial velocity? So yeah, it's a design problem. So off we go again. Now, as usual, we write v is the first derivative of the function we're interested in, which is x, and differentiate both sides again, and you get that dv dx is equal to the second derivative of position. Now, to be honest with you, it's a bit easier here because this makes sense. This is velocity, this is acceleration, which is the derivative of velocity, but there's no harm kind of doing it kind of in a dumb way like this, because when you get to something that's maybe abstract or the first derivative you can't interpret it properly, you'll be stuck. You probably want to do this every time. So we write this thing as two first orders. So this is the differential equation for x, together with the starting value of x, which is 1. And the second derivative of displacement, in other words acceleration, is dv. Oh, that should be t. Sorry. T. So dv dt then is minus 25. And I just write x, I don't need the x to t here. And the initial velocity, so this question is actually set up in a way that it's not that I'm interested in, normally when you have a differential equation, you're interested in what's x, say between 0 and a half. Here I'm actually, it's a slightly different problem. I don't really care what's happening in between. I just want to find the initial velocity that does this. So this is, as we said, a design problem. So again, do Euler's method. It's picking a slope of 4. Now this is a stupid choice as far as I'm concerned. I mean, you want to probably shoot right at it. If I was to do this again, to shoot straight at it, it's starting at 1. After half a second, it's equal to 0. So rise over run is, I reckon I should have tried minus 1 is the rise, a half is the run, so minus 2 would have been a better shot. I don't know why I picked 4, that was kind of stupid. So anyway, if you do it with 4, which this does, it doesn't make it close in half a second, but you can use goal seek. So I think here B52 is the displacement, maybe I'll just put x and v here. So this is t, x, v. So set the displacement after half a second equal to 0, as I want, by changing C2, which is the initial velocity. Do the goal seek, press the button, need this. And it turns out that it works with, so shooting straight at it doesn't work. Of course this doesn't work because if you're shooting the spring closed directly at it, well, there's a displacement, so there's a hook force, and that will speed it up. So it's already got a speed of 2, velocity minus 2, speed of 2, it's going to speed up. So this is going to get more dramatic and it's going to close too quickly. So it turns out you have to actually push this spring open a bit, because left to its own devices, actually, even I'd say initial velocity of 0, it will close too quickly. You have to give it a bit of a push, and then it comes back. So there might be a suggestion, actually, if you're really thinking about this as a design problem, if you want this spring to close in half a second, you don't want to start by pushing it open. That's, if you think that's bad for so many reasons. So really what you want to do is get a weaker spring. That probably makes more sense. So actually a better design problem altogether is have the initial velocity equal to 0, and you've k in a fixed thing, and keep changing the spring constant until it closes on its own in half a second. And then I suppose this is the thing, Obviously this is an exactly solvable problem. You can do this with Marina's maths and you can find out the period. It'd be like 2 pi over omega. Omega is square root of k over m, and you can actually solve it. The word is analytically. So this is a lot of palaver over something that can actually be solved exactly. But anyway, we'll keep on going. So it turns out if the initial velocity is 6.64, this will do it exactly. So here we see this one is the velocity. And then this is the displacement. And you can see it closes in half a second, but as I said, the spring is probably too strong because we have to actually push it open initially. And I suppose I have this example here, but realistically we looked at this design issue earlier in the module, so it's not too important. Okay, that's goal seek for the shooting method. So our second chapter that we're interested in is partial differential equations. So partial differential equations are far more difficult than what's called ordinary differential equations. So in partial differential equations, the function that you're interested in doesn't just depend on one variable. So for example, we've seen maybe displacement depending just on time, velocity depending just on time, we've seen temperature depending on distance, bending moment depending on distance. This is mostly what we've been concerned with. But as things get more interesting, you have functions depending on multiple things. So for example, 2 examples would be if you have a plate, a 2-dimensional plate, the temperature, the input isn't a single number, but a pair of numbers, coordinates x and y, where on the plate. And so you have a differential equation where the solution is a function of 2 variables, say x and y. Another example might be if you have a rod, and we mentioned steady state temperatures. What about a rod that's initially cool and is heating up? Then the temperature depends on 2 things: how far along the rod you are and what time it is. So when we've got this situation where a function of several variables, you're into partial differentiation. Now, with ordinary differential equations, you can kind of solve them exactly, and then in this module you learn how to solve them approximately. We do things the other way around for partial differential equations. You're not going to learn how to solve partial differential equations exactly until 4th year, and you're going to use, as far as I understand, a mixture of Fourier series, I think, and also the Laplace transform. But in this module we'll see where partial differential equations come from. We're going to derive 2 partial differential equations. The Laplace equation, which basically describes the steady state temperature now we'll do 2 dimensions, but it also works in 3. And we'll also do the heat equation, which describes how temperature changes in time, and the temperature is distributed across something. Okay. Now what we're going to do is, we are going to derive these differential equations, maybe one of them today, we'll see. But the big story is, rather than taking, like we did in the first chapter, a differential equation, an exact differential equation, and solving it approximately, what we're going to do in this chapter is slightly different. We're going to take an exact differential equation and we're going to approximate the equation. So we're going to turn differential equation into what you might call a discrete equation. And this is very important in engineering, so there's things you can look up. There's finite element methods, finite difference, all these kind of things. Basically, difficult problem, we'll see what we do. In theory, you can solve these approximate equations exactly, but actually we won't bother. We'll take a partial differential equation, approximate it using a discrete equation, and then we'll solve the discrete equations using numerical methods. But we can make the errors very, very small, so it's no problem. Now the big thing, how do we possibly approximate equations is use finite differences. Okay. Now there's different things I can write here. Ultimately, there's formulas down the bottom here. There's actually another formula missing, I think. I'll put it down the bottom. Now there's different things written here. Maybe up the top, we'll write down the definition of a derivative. Okay. So the definition of a derivative, if y is a function of x that can be differentiated, f dashed of x is equal to the limit as h tends to 0, f of x plus h minus f of x divided by h. Now what you can do here, now there's different ways of thinking about this, but okay, one of them is the top is a change in f. Now if you should at this stage really from last year